When we're starting with Java, it's important to start out thinking about object types in particular. You've probably dealt a fair amount, if you've done Java before, with primitive types, and some probably with object types. And once we start to think about objects, then we have to think about how memory is done in Java. So everything is an object in Java, except for the primitive types, which are sort of special cases. Objects are always handled in Java through references to them, meaning that they never contain in their line in memory in the stack their actual values. They contain a reference to some space out in larger sections of memory in the heap. Objects have to be explicitly created using the keyword new, with the exception of strings, which can have just string literals written in. They can have methods and attributes, also known as fields, data members, instance variables, lots of names for these. And they're accessed using the dot operator, like x.name, or calling the method x.getName. Objects have types, just like primitive types have types, but the type for an object is defined by their classes, meaning the Java file that says somewhere public class whatever, or private class for some that we'll see later. And that means that an object is an instance of a given class. We write a class called named ship, and then we can create variables of type named ship. And we can say, as we did above, something equals new named ship to create an instance of that class. So we have classes that are a general specification, what's possible for that type of data. And then we have objects, which are the real versions of this, sort of like the concept of what it means to be a person and what people are capable of versus a specific person living out in the world and having particular state and actions that they take. Some people will argue that there are no pointers in Java, and this is in some ways a fair statement. However, in some other ways, it's not exactly the right framework or the right statement. There are not pointers in the sense of you being able to manipulate the memory addresses of things the way you might have in C or C++, but there are references all over the place. When we say x equals new named ship, we're creating a reference to some named ship object out in memory. And then when we say named ship y equals x, we are creating a second reference to that, like a second pointer to it. And if we change the name of y, if we set name for y, we are changing it in that one referenced location, much like if you've worked with pointers before, that change would be reflected for all of the pointers. So no, we can't manipulate memory the way that we could in C or C++, but yes, we do have references. We sort of have pointers. There are kind of pointers everywhere, all over the place, and in fact, the name variable inside of that named ship object is also a reference. And so we change the reference to some other string. And when we talk later about how that memory is actually handled, we'll see that we don't have to mess with all of the pointery gunk that we might have had to in C or C++, but it does change the reference and it does point away from it now. So there are modifiers inside of classes that can apply to attributes, methods, and in fact classes themselves. We can make public, protected, or private variables inside of a class. We can make public, protected, or private methods, and we can also make classes with different visibility to them. So that's one modifier, is visibility, whether it's accessible everywhere, being public. If it's got nothing, then it defaults to being accessible within a package, and we'll work a little bit with packages in our projects in the class. If we make it protected, it's accessible to anything that inherits from our class. And if we make it private, it's accessible only inside the body of this class without accessors or mutators like get and set methods for it. And even then you can't access it directly. There's another modifier that you may have worked with a little bit, which is static versus non-static. It's a little tricky because static is the only explicit one you write. You write that it's static, and if you don't write static, then it's non-static. So it will be an instance version that time. Whereas static things belong to the class. So if I say there is a static list of all accounts, then that belongs to the bank account class. And so there's only one list of all accounts, thankfully, because a list of all accounts should only have one list of all accounts. So that allows us to track something for the whole class. We can do similar things of like counting how many times a class has been instantiated by incrementing some static integer for it. It can be accessed, static things can be accessed through an instance like we normally would, like x dot something, or through the class itself. So here we can say account.allAccounts, or we can say bankaccount.allAccounts. Both of those are legal. The visibility of it may differ, it may be public or private, so where we can use those may differ. But for a static variable, there's only one version of it for all instances of that class, and it can be accessed both through instances and through the class itself. Another important thing about classes and objects in Java is inheritance. And you've probably seen this in other languages if you've done other object-oriented things, but we can take a class B and have it inherit from a class A, which essentially reuses some of the code from class A. It gives B some of the stuff that belonged to A. In fact, all of the stuff. So we can say that B is a subclass of A. Some people will say B is an extension of A. Some people will say B is a descendant or is a child class of A. Essentially, what that means is that methods and attributes that were defined in A will exist in B. They may not be directly accessible, but they will exist. And we'll see some examples of that. New attributes and new methods can also be added in the class B. So we could add a new method that was never created in A, and now B has that functionality, and A will not get it necessarily because this is a one-directional thing. B gets stuff from A, not the other way around. You can also redefine things in B that existed in A. We'll do this for several different methods, and you've probably done it before, whether you know it or not, if you've done Java and you've written classes. It gives B a different behavior for the same method of signature, or signature of method, or we can do this for variables as well. When it's done for a method, it's called overriding, and when it's done for a variable, when you create a variable with the same name in B, that is as a variable that existed in A, that's called shadowing. We shadow the parent's version or the parent's name of that. And so it gives preference to B's version of that method when we override, or that variable when we shadow. The old version of a method still can be used in the definition of the new version, or it can be used in other places in B. We use the super keyword to reference the parent classes or the superclasses version of something. We should use inheritance when we could state a sentence that B is a A. B is an A. For example, rectangle is a shape, and therefore it would make sense for rectangle classes to inherit from shape classes. But if it is something like person has a name, that is not an inheritance relationship. A person is not a name, but a person has a name. Well, that would just be adding a variable to it. People often get confused by these, but if you can state it that something is always another thing, then we can use an inheritance relationship reasonably there. In Java, there is only single inheritance for class to class. And if no ancestor is specified, a class actually inherits from the object class that is built into Java. When we do inheritance, we can get this neat behavior called polymorphism. And so this is what we talked about before, where we can override or we can shadow something. Here we see A has an integer x, and it has a void method called status. A's constructor just sets A's x to be whatever the parameter was that was passed in, and then B extends A. So B inherits from A, which means it could just get status and x for free from A and use them. But if B needs to have its own versions of these things, which I would argue often it does for methods and very rarely it does for variables, for fields, you should almost never shadow, but you can quite often override. These are good rules for this, generally speaking. So when we shadow x, we create the x in B. This is a new attribute that inside of B is just going to be called x. And if we try to refer to x, we'll only be referring to this closer one that was defined in B. We can refer to the x from A using that super keyword. And the same is true for status. We created a status method that has the same signature as status over here. So that's called overriding status. We can call to the parent version of status by calling super.status, and we do here. So that will mean that we do everything that's in the parent version first, and then we start doing the stuff that's in this new version, this overridden version here. And then we see also that B's constructor calls to A's constructor. This should always be done as the first thing inside of a child class. If you need to explicitly pass something to the parent class, you should do so very first thing. And then you notice what B is doing. It's adding 1 to its own version of x. So this will modify the local or the shadowed x here. It won't change the A version. If we had not shadowed it, then that would change the A version, because the A version is the only version that exists in that world where we didn't make a new x here. So my main method down here creates an A with the value 1. It creates a B with the value 10. It creates a variable called C that is of type A, because remember, we can take the parent type and we can store A objects in that parent type, or we can store B objects in that parent type, because B is an A. And so we're able to put B's into an A container. If we did the rectangle and shape, we would be able to put rectangles into containers that are labeled shape. We can put rectangle objects into variables that are called shape. So when we run this code here, what we're going to see is that for the first one, when we call status and then we do the print line here to actually directly access the x variable, we're going to see that x is 1 because we're in the A class where x is just whatever was passed in. We passed in 1, so x is 1 is printed out by the status method. And then c.x equals 1 as well, meaning that we're accessing the A version of that. The other part is where it gets a little odd. So we've created a B object and given it the value 10. That would call to B's constructor with the value 10. B then calls to the super constructor, meaning A's, with the value 10. So the AX will get set to 10. Then it adds 1 to the BX. It says this dot x equals x plus 1. So that will make it 11 inside of the B class, 10 in the A and 11 in the B. Now, when status is called, what it will do is it will call to super.status, which prints out x equals 10, the A version. That makes sense. Then it will say and new x equals 11. The B version. That also makes sense. It gets a little funny here. It says c.x equals 10, calling back to the A version of it. So when we call the method, an overridden method will be chosen by object type. The object we created was a B object. And so the overridden method will get called here. The B status will get called here. But when we refer to a shadowed variable, the variable is chosen based on the declared, the variable type. So C was declared as A. When we say C.X, it will look it up in the class A because A is what it was declared as. If we tried this with the B, lowercase b object here, then it would only access to the B versions of things because it would call status based on the object type, which is a B, and it would get X based on the declared type, which in the case of the lowercase b variable is type uppercase B. So this is part of why shadowing variables is bad and confusing, that the variables will get referenced based on the declared type of the variable that you're using. So we declared C was an A. Any of the X, Y, Z variables that I'm looking up for it will be looked up in the A class. Whereas what we really were hoping for was to override that stuff, make it so that B behavior happened. And so with methods, we do see that in Java. We see that if B has a status, and I call status on this thing, I'm going to call B's version. Taking my rectangle and shape example again, if I create a shape variable called S, and then I say it equals a new rectangle, when I ask for the area, I'm wanting a rectangle calculation for area, not a shape calculation. I don't even know what a shape area calculation would be like, but I want it to give me a rectangle version of the area. And so from methods in Java, we get that behavior that we probably wanted. We overrode the method, and therefore we probably want to call the overridden version of the method the rectangle-specific area or the B-specific status. We'll get that from methods. We will not always get that from variables. So it's not great to shadow variables. You get weird behavior. One way in Java that we can do inheritance, sort of, is with interfaces. It describes the visible parts of a class, but not the inner workings. So it describes them as a public set of methods and possibly some public static constants. Typically, an interface is mostly going to define the method signatures. It may also come with some variables like static constant variables that are useful for all things that are going to use that interface. It does define a type, much like a class does, but it then is implemented in classes, and you'll do this for some of your homework projects. It alleviates some of the limitations that Java has of single inheritance without adding complexity of where you're going to get the behavior from. So what that means is it says, for instance, that if square is an interface, all things that implement square are going to have a side method and an area method. Okay, that makes sense. Now, is it going to be a square that has color? Is it going to be a square that can be scaled up and down? Is it going to be a special case of square called a rectangle? Which of these things, or rather, we could do the other direction, a special case of rectangle that is a square. Can't go the other way. But we can create versions of square that implement this interface, and then we can count on them having a side method and an area method. How will they do those? I don't know. That's specific to the class. For instance, we could create, again, shapes, and then we could have that all shapes have a draw method so that we can cause them to draw on the screen. How are those shapes exactly going to be drawn? Are they going to need a radius or a width and a height or whatever? I don't know. But I do know that I'll be able to tell them to draw, or I do know that I'll be able to tell them to calculate their area or various things like that. So an interface is sort of a contract that we sign and say, my scalable square class will follow the contract of the square interface. And that allows us to guarantee that that behavior will be there if we have a variable of type square or a variable of type shape in my other example. There are also in Java abstract classes and abstract methods. Abstract methods are similar to what we saw in the interface. They're methods that just have their signature, their headers, without any implemented bodies. We know they're going to look like this, but we don't know how they're going to function just yet until we get to a class that inherits from it. and then we'll define it there. If a class contains at least one abstract method, then it must also be an abstract class. Because if you don't know how some of its functionality is going to happen yet, then you're not going to be able to create instances of that class. I don't want to create instances of shape if I don't know how those shapes are going to calculate their areas. I can create variables of shape, but I cannot create instances of it until I know all its functionality. Java's not going to let me run code that I haven't said how it works yet. A class can also be declared to be abstract, even if none of the methods are abstract. You can just put abstract up at the top of the class, like down here, and it'll make that class abstract, which essentially means you cannot create instances of it. Abstract classes can be extended into concrete classes by providing an implementation for any of the abstract methods. So again, I could write shape as an abstract class where I give it some of its functionality. Some of the methods might have actual bodies, but things like area, I don't know. I don't know how they're going to work. So I write those to be abstract methods, saying I'll implement those when you tell me what kind of shape I'm implementing, or when I decide what kinds of shapes I'm implementing. Triangles, squares, rectangles. We'll figure it out. And so when you go to those other classes, then you're going to make the actual implementation for those. All methods in an interface are by default abstract and public. They have to be. That's the whole purpose of an interface. We don't have to use those keywords as we saw above in our interface example, but those methods are already abstract and public, meaning I assume there's no definition and they have to be public just as part of that interface contract. So here I've defined a simple abstract class that is a stack and it has a pop method. I don't know if that pop is going to look something up in an array or whether I'll use a linked list or what I'm going to use to do the magic of the pop function there. But I know that my all stacks will need a pop, and they'll choose based on their backing data structure what exactly their pop will do when they are non-abstract classes that implement this stack class. It's reasonable to think that a class that had no data members and only public abstract methods is going to be treated the same as an interface, but by Java, it's not quite. It's got the same stuff as an interface, but Java is going to treat it slightly different than an interface. For instance, you're going to be able to implement multiple interfaces, but you are not going to be able to extend multiple abstract classes. Let's look at some examples of implementing some of these behaviors, overriding some stuff in Java that you may have even done before if you've worked with Java. So one thing that you may remember is that double equals is not exactly what you always want between objects in Java. When we do double equals, we're actually looking at that one line in memory to see that that contains the same thing. So for integers, that's great, because if an integer is 3, its one line in memory is going to contain 3, and another integer should contain the same value 3 to be compared and equal. So they're stored by value, but objects are stored by reference. So when we do equals, double equals, for Java objects, what we're saying is the reference in X must be the same reference as what's in Y. The memory address for X should be the same memory address as Y. This is like saying whether you're talking about Steve or my friend, you're talking about the same person. Are we? Okay, that's what you're checking with double equals. Are they actually the same person in physical space, or the same identity there? Whereas dot equals is what we typically want when we're comparing to see if two objects have the same stuff, if they're equivalent. If two strings have the same characters, we call dot equals and it returns true. So dot equals is the comparison that we often want to do for objects, and many programmers make this mistake, right, between double equals and dot equals. It's common in lots of languages, especially ones that have object orientation and sort of reference versus value types like these. So we can actually override the equals method. The object class just goes ahead and calls double equals if you do not define an equals for your specific class. Well, that's not typically what you want. So if I make my shape class, then, or my square class, for example, what I really want when I call dot equals is to check that those two squares have the same side lengths. But what I'm really probably going to get if I don't override equals is I'm going to call the version from the object class accidentally, and it will check double equals, it will check memory equality the same as I wanted to avoid before. So the default behavior in Java, if you don't write an equals class, is it's just going to call double equals. Well, we can override this in our square class, for example, to implement our own version of equality. The trick is there are 3 methods in Java for all objects that you want to make sure are equivalent or are matched up to each other. So they are equals, hashcode, and compare to. For instance, you've probably seen compare to before. It returns a negative value or a 0 or a positive value depending on whether things are less than, greater than, etc. Well, if equals returns true for 2 objects, then compare to had better return 0. And if the hash codes if 2 objects return true for equals, then their hash codes should come out the same too. So we need to keep some consistency between these 3 different things because they may get called internally by Java to do different operations. For instance, if I check if an array list contains something, it might call equals. And if that's not consistent to my compare to or my hash code, then I might run into problems when those compare to and hash code are called on those things that were claimed to be equal. So I need to keep kind of a grouping of these. Here's an example of an equals definition. We might have the book class here, which has a title and has page numbers. And we might state that 2 books or 2 objects represent the same book if and only if they have the same title. So we're checking titles essentially. But if we called dot equals on this class as written, it would check memory equality. It would check that 2 things are the exact same thing in memory. So if someone comes in with a second copy of the same book, those would not be memory equal. Those would be 2 separate objects. But what I really wanted to know was, are they handing me a book that I already have? So we can design an equals method for the book class by, for instance, overriding the equals object method that belongs to the object class. It does have to be object here so that it matches the signature. And so what we do then is we cast to a book and we check the title and we check that that title equals the other title, or rather equals this title. So we're just comparing the titles of 2 books, assuming that that object we were handed was a book. If someone tries to hand us something that is not a book in this example, we will get an exception. Our program will crash or will at least report this exception. That's a class cast exception. I've tried to cast to be a book, but it's not a book. So if we compare a book to a non-book with this version, it's going to blow up our program potentially. Another solution is to do a try catch on that. So try returning whether the titles are equal. And if it's a book, that will work perfectly. And if it's not a book, we'll return false. So this allows people to pass in things that are not books, but it will only tell us they are equal if it is a book and it has the same title. So it will sort of handle that problem. There's a third solution that's actually a little more efficient, but is the same as our solution 2. And that is to check whether O is an instance of book and then return the title comparison there. It is a little more efficient than all of those exceptions having to happen and get caught and things. It is a rare good use of the keyword instance of, which checks, does O have the type book? Okay, it does. Let's proceed forward. People often try to use instance of in very hacky ways to try to differentiate behavior in their code when you really shouldn't most of the time. But in this case, it's actually okay. It's a good use of it to quickly check, is O a book? If not, I'll just return false. And if it is a book, then I'm going to compare the titles. And one final way that we can do this is to actually use sort of a mix of overriding and creating new methods. So we have to override the object version, or otherwise we won't have actually overridden it. It will just call to the object version of it again and do double equals. But we can say that we're overriding the object version. And then down here, what we're essentially doing is we're doing that instance of check, and then we're calling to a book-specific version. And that will call up here to the other one, and then it will check the titles against each other. This avoids the casting inside the method, but it does have to cast here to make it into a book. So that's another possible approach to this. As I mentioned before, if equals is true for two objects, so if x dot equals y gives us true, then x's hash code should be y's hash code as well. This is not true for the default Java version of hash code because that's based on the memory address when you call it for an object in general. So we'll override hash code. We will call to the title's hash code, and since the title is a string, it has a hash code function. That will work just fine for us. So then I'm able to do things like create this hash set of books in which I put in a copy of Moby Dick, and then I have some other copy that someone walks in with and says, would you like to add this to your library? And I can ask if my library already contains that book that they've tried to hand me. If I overrode hash code, then my library would come back and say, yes, I already contain that, so you don't need a new version. But if I did not override hash code, then I will get false back, even though those two books are equal, even though my equals method would return true for the two of them. Because it's a hash set I'm using here, it's going to call to hash code automatically in the background and check whether the hash codes match. They won't because they are not memory equal, these two here, so they'll get different hash codes. So, and similarly, if we're implementing the comparable interface, then we should also override the compare to method to match whatever we've handled for our equals and our hash code. Here are some common mistakes that people make when overriding methods. One of them is to try to override only specific to the type you're doing. This doesn't override because it doesn't match the same signature as the object class has. The object class takes an object as its parameter. Therefore, our overridden version must take an object as its parameter, or otherwise this one may not get called when we try to compare two books. Another common issue is to do memory equality inside of the equals, but these are strings. Titles are strings, so we might miss and do memory equality and miss something that should be equal. Misspelling the method that you're overriding. Java will gladly allow you to create that new equal method, but it will not override the equals method because it doesn't have the same signature yet again. A similar thing is capitalization, forgetting which things are capitalized. Hash code has a capital C, so again, it does not override the original version. So here's sort of a fleshed out version of making sure that two objects are representing the same book if and only if they have the same title and will add in the same number of pages. Maybe a different edition has a different number of pages. So we've done the version where we override the object one and we write a special one for books so that it's called to inside of the other. And we check the titles against each other and we check the pages. And we've overridden hash code still so that it would be true. However, we should still update our hash code so that the hash codes are the same in the same conditions as we had here. The title and the pages should match. So we're doing a little bit of modification to make sure that our hash code contains information about both of those. And now, finally, we've overridden this behavior from the parent class of object, and it's one of the beautiful ways that we can use object orientation to get new and interesting behavior in the classes that we design.